Alrighty then. Okay, so welcome. Um, it is just after 7, so I am gonna get started. I did not see online that anybody posted any specific questions about this material, so I think I'm just gonna kind of do a review of like all of the different like bits and pieces of what's going on. And of course, feel free to email me with any questions that you may have. Okay, so this midterm is covering sections 7.1 through 8.3, I believe. I'm not the expert on this, but this is what I think it is. So we're going to start in 7.1 and just kind of work our way through and remind ourselves like exactly what we're going to be tested on. Okay. So 7.1 is sets. And so here we were basically working with a lot of set notation, and we learned a lot of new notation and like ways of like writing things. Particularly ones that we use later on, symbols that we'll use. If we have a set that is A and then we have a set that is B, we know that this is the union of A and B. So if A is equal to 1, 3, 4, and B is equal to 2, 4, 5, then the union of A and B is going to be equal to 1, 2, 3, 4. So we know that union basically means what's in both of these. Intersection is going to be basically what, instead of like all of the numbers in both of these, the ones that are shared between those limits. All right, so that's some of the basic notation we learned in section 7.1. We also talked about the complement of a set, saying that, for instance, A with a bar on top is going to be everything that's not in A. So let's say that this space is equal to 2, 3, 4, 5. So we're not really going on 6, 7, 8, 9, 10 here. Then everything not in A is going to be 2 and 5, because those are the things that are not inside of the set that is A. Okay. All right, and then let's talk very briefly about and so De Morgan's properties are going to be the statements that look like this. This is from page 363. So if you want to go and freshen up on this theorem. So this is true, and this is true. I think you guys have talked about this already, like earlier in the semester. Just like for the sake of like going over it right now, we know that A union B is 1, 2, 3, 4, 5. We know that A naught is 2, 5. We know that B B naught is going to be equal to 1. Sorry, B naught is going to be equal to 1, 3. And so what is the intersection between them? Well, there is none because none of these numbers are the same. So we're going to say that A union B, the complement of that, is going to be 0, which makes sense because if we try to take, if we're saying that there's only 5 numbers in this space, which again is the limitation that I had to put on here, just to make these examples kind of logical. Then the union of A and B, the complement of that is just going to be 0 because there's not going to be anything in that sample space. Okay. So a lot of 7.1 questions were just asking us to like work with these sample spaces. So let's talk a little bit about 7.2. This is number elements in a set. Okay. So basically what this is talking about is basically like adding some numbers into this mix. So we have the counting formula, which says that n A union B equal to n A plus n B minus n A intercept. And this is basically just logic, because for instance, if we were to have our same sets as we had last time, A is equal to 1, 3, 4, B is equal to 2, 4, 5, there's going to be 3 numbers in A, 3 numbers in B, 1 number that's common between them, and so the union of A and B is going to be 5 numbers. So it's basically just a logic problem. And a lot of these things are basically like that. If it says like the counting formula, it basically just means you need to know how to count. Okay. Then 7.3. So this is the multiplication principle. And so basically what this is saying is that you can multiply probabilities together in order to get like the end probability. And so this is basically where we started talking about the tree diagrams that we've been using so frequently lately. And so the multiplication principle basically is talking about like if there are so many choices for this, they're not specifically talking about probabilities here. So let's say there are 3 choices for this, or 2 choices for your second choice. I don't know what you're putting on in the morning. So this is shirts, and this is shoes. How many combinations do you have? Well, the amount of combinations you have is going to be 3 times 2, because there are 2 options for shirts and 3 options for shoes. That's going to be 6, which matches up with the 6 different prongs at the end of this tree diagram. So this is where we start kind of like looking at tree diagrams More specifically, let's do a couple problems from 7.3 just to refresh ourselves. Okay, so we're going to do number 6. Oh no, that's a skill builder. We're going to do, we did that one in an earlier GSG. Sorry, I was planning on doing one, but I'm reading it now and I'm disliking it. So, okay, so we're going to do 22, which is talking about car insurance. So the problem goes, Sean is purchasing a used car for college and needs to obtain liability insurance. His insurance company offers 8 levels for bodily injury coverage and 6 levels for property damage coverage. If Sean must carry both types of coverage, how many different liability policies does he have to choose from? So basically, he's going to be choosing one from the one different level from the bodily injury and one level from the property damage. So he's going to pick one of 8, and then he's got one of 6. So it's basically just going to be there are 48 different potential coverages. Okay. Let's also try number 33. So this is saying how many, part A, how many different ways are there to arrange the 7 letters in the word problem? Okay, so basically how we're going to do this problem is we're going to set it up thinking, so we're going to have one letter that we pick right away. And it's basically going to be, I have 7 options. So 1, 2, 3, 4, 5, 6, 7. So it's not a very pretty tree diagram, but it's what we got right now. So there are 7 times, after we make our decision for 7, there's going to be 6. And then after we make our decision for the next letter, or there are 7 letters in problem, yeah. Yeah, oh, there are 7 letters in problem. So then we're going to pick, there are 5 remaining letters, then 4, then 3, then 2, then 1. And so we're going to do a little bit of math here. So you can see I just did like some multiplication here on the side, and there are going to be 5,040 different ways of spelling the word, or not spelling the word, but organizing the different letters in the word problem. Okay. So I think that pretty much kind of like reviews 7.3 and the multiplication principle. So let's talk about 7.4. So this is sample spaces. Okay. So basically this is talking about like how to like divide and how to like think of different like probability like options. We did a lot of problems with dice. We did a lot of problems with like so many children being born, and are they boys or are they girls, and like what are the chances. We did a lot of problems with like coins being flipped. So basically what you need to know is like what a sample space is, and that it's basically like all of the possibilities that can like possibly happen. For instance, if I were to flip a coin twice, I could get heads first, I could get tails first. So let's say I get heads first, and then I get tails first, and then I could get heads again or tails again, heads or tails. So the sample space has 4 things in it: heads, 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 tails, tails, heads, and tails, tails. This is what's in this sample space. So basically a sample space is like what can possibly happen. That being said, then it also like talks about like what the probability of the outcome is going to be, which is basically like what stuff that we've been working with for the last few weeks, how to construct probability models, and then we also have this theorem on page 384 that I just want to make sure we talk about very briefly. This is all like outcomes that are equally likely. So if the sample space has however many equally likely outcomes, and the event in E in S contains n outcomes, or m, then the probability of event E, written as PE, is the number of outcomes in event E divided by the number of outcomes in S total. So for instance, like if we were to apply this to our coin flipping that we just talked about, we have 4 in sample space S, so n is equal to 4. If I want to say what are the chances I get heads and tails, I don't care about order. These are the 2 that have both heads and tails, so m is equal to 2, and the probability of me getting both heads and tails is going to be 2/4, or 1/2, which makes sense. Again, a lot of these theorems that they say are basically just common sense things that I'm sure like is very intuitive to you by now. Okay, let's do a couple problems from 7.4. For instance, let's do 17. So how many outcomes are in the sample space associated with tossing 3 dice? Okay, well, in terms of this, order does matter. So there are 6 outcomes for the first dice. There are going to be another 6 for the second dice, and another 6 for the third dice. So the sample spaces will look like this: 1, 1, 1, 1, 1, 2, 1, 1, 3, so on and so forth. And we're going to end up with 36 times 6. So it's 216 different. So this would, I'd have to write down 216 different numbers to like make the full sample space. So it gets pretty big. Okay. What about selecting 2 cards in order without replacement from a regular deck of 52 cards? Okay. So this is 19. Okay, so we're taking 2 cards out of the deck. And there's 52 cards in the deck. So this first possibility, if I were to draw a tree, there would be 52 possible cards times 51 possible cards because we didn't replace the first card. So the answer to 19 is going to be 52 times 51. Give me a okay, so 52 times 51 is going to be 20. I just wrote it down. Where did it go? It's going to be 26, 52. Okay. So that's kind of like the basics of like thinking about sample spaces. We did a lot of problems regarding this, making sure that we were like keeping track of how many sample spaces, what the sample spaces were, et cetera, et cetera. 7.5, we got into probabilities of events. And basically, we talked about mutually exclusive events. Like what does it mean if an event is mutually exclusive? So like if there are 2 events, or not an event is mutually exclusive, but 2 events are mutually exclusive. Like if I have 1 baby, can I have a boy and a girl? No, I only have 1 baby. So no outcomes are in common. That was a poor example. That was, in my opinion, that was a poor example. I'm sorry about that poor example. More of, I don't know. I'll come up with a better example in a sec. I know there are like a million in the book. Okay. So basically, the rule associated with mutually exclusive events is that the probability, so our events are going to be E and F. The probability of E or F occurring is equal to the probability of E plus the probability of F. And so this is less about like how to tell if they're mutually exclusive and more about what you can do if they are mutually exclusive. What section is? Sorry, give me a sec. This gets a little bit into, apparently, can't find it. Okay, never mind. This is fine. Basically, 2 events E and F are mutually exclusive if there's nothing in common with them. So it's less of okay. The example with the baby, I need you to forget that the gender of the baby doesn't matter. That was very section 7.4 of me to come up with that as an example. Rather, let's say 2 events are mutually exclusive if I go over across the room right now and I draw a card out of a deck and I look at the card and I'm like, okay, I have this card. And then I walk back across the room and I roll a 6-sided die. These 2 events have nothing to do with one another. And so the chances of me getting a red card and a 1 are going to be the chances of me getting a red card and the chances of me getting a 1 on the dice, because there is nothing in common between them. So they are independent events. They don't have commonality. Okay. That being said, basically another thing that we can consider in this chapter is, they call it the additive rule. Basically, they're saying that if you have two probabilities, they equal each other minus what they have in common. Okay. And then in addition, this is, in my opinion, probably one of the more important things that you should remember for this exam that's coming up. If you haven't already taken it, that's really ugly star. That's fine though. The point is that this is noticeable. This is the complement of the event. So the probability of E not happening is equal to 1 minus the probability of E happening. And why does this work? Well, we know that the probability of something happening is 1. So this is like generic 100% probability. This is gonna something's gonna happen, whether it be event E, event F, event G, whatever. Something's happening. Sorry. Okay. So basically, 1 is an event happening. 1 minus the probability of E is the generic probability of not E. And so this is going to be a rule that is extremely useful in a huge amount of cases, and I would highly recommend you just know by heart. So they call it probability of the complement of the event. I would just say there's a certain amount of logic to it as well, but important rule. Also something to look out for, because in terms of the exam, there are certainly times when on the exam they'll say, what are the probabilities of this not happening? And so you have to go through the whole process to say, okay, so this is the probability of it happening, and however many steps you have to do to find that, and then you just 1 minus the probability of it happening. And the probability of it not happening is a lot more complicated to do. So if you're looking for the probability of something not happening, event E not happening, some other event not happening, please just default to this rule, unless there is some sort of a reason why it's more inconvenient for you to do this some other way, because this is a favorite of testing. Okay. This section also contained odds for E and odds against E. So odds for something is the probability of E over the probability of E not. And then odds against is the probability of E not over the probability of E. And basically, you need to associate odds for with probability of E to probability of E not, and odds against with E not to E, because if you don't go through and make that association before you take the exam, it's going to be really easy to get these mixed up. Okay, let's talk about section 7.6. This is value. And basically, this is saying that we can find what we think that the generic value is going to be. I remember talking about like the lottery with you guys very like generically when we were going over this section, and I said the expected value of winning the lottery, like if I go in and I spend $5 on a lottery ticket, my expected value is going to be like, I'm going to lose like, I don't know, $4. And the reason the expected value is that I lose $4 and not $5 is because somewhere somebody won the lottery once, and the chances that I win the lottery are very small, but the payout is very big. And so expected value is basically balancing chance with payout. And so the definition of the expected value is equal to m1 times p1 plus m2 times p2 plus m3 times p3, where m is going to be the payout or payoff, and p is going to be the probability. And so if this is $1 million and this is like 0.0001, and then this is $100 and this is 0.01, so this $1 million is going to weigh a lot less on the expected value, but it's still going to have a pull. Okay, so expected values, very useful. A lot of the times you'll hit an expected value problem and it'll say, is this fair? And basically, if they're asking you if it's fair, they're asking you, is the expected value of this game that we're playing going to be 0? And a lot of the times it is just analyzing a game and this sort of thing. If you look through like the different problems in the book, you've got analyzing a game, raffles, like sports. It's all just very, very game. Roulette, that sort of thing. Okay, so chapter 7 in general is just introducing you to the general ideas of probability. So tips I would have for you for tackling a chapter 7 type problem. I would definitely take the time to kind of think about what sample space you're working in. You may not need to have like come up with a number, like this is how many probabilities are, or this is how many like options are in my sample space, but it's definitely at least a good idea to consider, like, what does my sample space look like? Is my sample space exceptionally large? Is my sample space exceptionally small? And think about how that might affect like the way that you approach the problem. Because for instance, if your sample space is really, really big, like in the thousands, why on earth would you ever like start by like thinking about a tree diagram? Because that's not going to like do you much good if you were going to use that as your main tool of problem solving. The next tip I have is to not panic, probably. Lots of this is just logic. For instance, the multiplication principle is basically just like you can like multiply things to end up. If you have 5 shirts and 3 shoes, then you have 15 different options that you can do. 5 shirts, 3 shoes, and 1 pair of pants. You're going to wear that same one pair of pants, and there's still going to be 15 options because you can mix up your shirts and your shoes, but not the pants. So it's a very like logical thing. If you run into a problem and you're not sure what to do with it, you're not sure, like, is there a rule that you're supposed to use? Or you like, basically what I would recommend you do is you stop, you ask yourself, what does the question want? What do you want from the, like, what are you looking for? What information are you looking for? And what information do you have? So when I am working with a particularly rough problem, set it up by saying, this is what I have, and this is what I want. And that helps me kind of organize myself. And if I write out everything that I have, I might realize that, oh, I can just multiply these numbers together, or I can find the union of these, or there's usually some form of problem solving that you can do once you lay out all of the information you have. So those are my tips for probability in chapter 7. And of course, both of those apply to chapter 8 as well, which we're going to talk about in just a sec. There's still nobody here in the GSG, so I can't ask if there are really any questions, but this is a reminder that one of the best things you can do to prepare for an exam is practice problems. Or I guess I didn't see if you had a practice exam posted, but if there are practice exams, then I would definitely recommend that you track down a practice exam and try to work through it, because like knowing the kind of problems that are going to be on the exam and knowing that you can solve problems like them is definitely like a good place to be at. Okay. So, section 8, chapter 8, section 1 is conditional probability. So, this is conceptually something that I personally, like, sometimes, like, struggle to, like, look at the notation and, like, come up with, like, the best, like, understanding of what was happening. Basically, what we're saying is that if we have this, it's E given F is the case. And we know that the probability of E given F is the case is going to be the probability of E intersecting with F. So like what are the similarities between E and F divided by the probabilities of F. Because I'm gonna write this in a different color because if the probability of E intersecting with F equals 0, aka they are mutually exclusive, aka they are independent. Well, not really independent. Mutually exclusive and independent aren't quite the same thing. But they are mutually exclusive. Then the probability of E given F will be 0. Because if F is the case, then E cannot be the case. Okay. So that is a very important concept from this section. Continuing on, you can morph that equation that I just gave you and say the probability of E intersecting F is equal to the probability of F times the probability of E given F. If this is information you have, you can use it to find this. This is just a rearrangement of the previous equation, though. Okay. So basically what this section is doing is having you do a lot of, okay, so what are E and F doing when they're intersecting? What are E and F doing like together? What are they doing apart? What are they doing if F is happening, can E happen? All of that kind of stuff. And for this section, I would recommend that you write everything down. Just if the probability of E intersecting with F is equal to 0.3, then write it down and make a list of all of the probabilities you know so that you don't get confused or lost. And then I would also recommend that I would also recommend that you say something using words, not just using the notation. As somebody who struggles with the notation myself, I need to write down at the beginning of this problem, I am looking for E given that F is the case, instead of just writing the probability of E given F. I need to very explicitly write down what I want in terms of actual words. So it's very important that you become comfortable with notation, especially as this class moves forward. But it's fine if you just say out loud to yourself or write it down, this is what I'm looking for. Okay. So section 8.2, independent events. So if two events are positive probabilities and the events are independent of another, basically one event does not impact the other happening. You know that really poor example that I had earlier when I was trying to talk about mutually exclusive events and I just ended up describing independent events? I really just was describing independent events, because what card I draw from a deck does not affect the roll of a dice that I make. And those are less mutually exclusive and more independent. They're not mutually exclusive. They are independent. So independent things basically have no impact on one another. Consider independent, classic independent example, flip coin. Flip a coin. Can we spell today? Guess not. And a classic dependent event is draw from a deck without replacement. Because then the probabilities change as you draw one card. It goes from, for instance, if you're drawing, if you're trying to get a red card and you draw one card, then instead of being 26 out of 52, it could be 26 out of 51 or 25 out of 51, and the probabilities start to shift depending on what you've previously drawn. So those are the two classic examples. So yeah, basically ask yourself, does doing this thing change the probability of doing something else? And if the answer is no, then it's an independent event, because however many times I flip a coin, chances are still 1/2 that it comes up heads and 1/2 that it comes up tails. Okay. And then finally, we hit Bayes' theorem. And so Bayes' theorem is talking, we used a lot of tree diagrams when we were doing this, talking about how can I like go back and forth between like E given, like they're using the notation E given A sub 1, and they're trying to find like A sub 1 given E. So Bayes' theorem very explicitly, in terms of like this notation, states this. Where PE itself is equal to PA1 times PEA1 plus PA2 times E given A2, you know, however many events there are. So basically, as we discussed last week, and you can see that last week I had a GSG session basically just talking about like what Bayes' theorem is and stuff like that. It's actually a pretty intuitive like situation, and what you're trying to do is go backwards on a tree. It's basically how I best like think of it. Saying, okay, so I'm like at this point, A, B, C, C. Okay, that's not the most important. And all of these have ABCs associated with them. So A, B, and C. Let's say I'm at A. So I know that I am at A. What are the chances that I came from this line, this line, this line, this line? How do I know the path that I took to get to A? And personally, I like to think of these in terms of like tree diagrams. I think of them as like forked roads. Like, okay, so I like am at point A, and how did I get there? I either did this path. So what's the probability of me doing this path? What's the probability of me doing this? What's the probability of me working through in this way? And so the probability of me working through these individual events is going to be the probability of this part happening. So the probability of AJ, or A1 in this case, times the probability of, here I am, this is our event E that we're looking at. So this is the probability of E given that A1 is the case. And so basically we add up all of these individual things, and to find the probability, and we add up all of these individual things, of which there are 4 here, and then we take the one that we're looking for. For instance, I want to know if I went through path A1, and then divide it by the total. And so that's the probability, which is like, would I have come up with that on my own? The answer is no. But now that I like look at the equation and I like see how it works, I think that it's like I feel much more comfortable with like what does this mean? How do I work backwards from one point to another? Anyway, point is about this equation. is that if you see something, if you have a tree diagram and you see something from the beginning, you're looking for the chances of, like, you know where you're ended, but you need to know how you got there, you're going to want to use Bayes' theorem. And that's what this A given E is. So that is all I have for you guys tonight. It's getting close to 8. So I'm probably going to wrap things up. Still no one is here, so I don't have any questions to answer. So I will reiterate my most important tips for taking your exam. Number 1, make sure you write everything down. Number 2, don't panic, because I promise you a lot of this is just logic. And if you start to panic, you become a lot less rational. So just like keeping a cool head is like number 1. And that's just like general test taking. But I would also highly recommend that you guys write down like everything. Like if it tells you you want to find, that's an eraser, not a P of E given F, then write down E given F, or E if F is the case, or whatever makes sense to you to understand what the probability of E given F is. Because what's most important is that you can look at this notation and translate it into something that actually has meaning. So yeah, that's all I have for you guys tonight. Thank you for watching this video if you're watching it later on. And have a good one, and good luck on your exam.